My project with advanced games programming, I am designing or rather recreating Capture the Flag. And a part of the process of creating Capture the Flag is to create a map which can support capturing flags and running routes. For the second assignment in advanced games programming, I am doing a design challenge that is around creating a Capture the Flag map with procedural content generation. And the procedural content generation itself is split up into a total of 3 systems, which consist of flattening a section of ground, mirroring the map, and creating cliffs to encapsulate the map so that our players don't fall out of the map, and this will include the enemy AI as well. The first system developed as part of generating a Capture the Flag map is to find a segment of land that we want to flatten. And to do that, I have chosen a methodology to choose one of 3 methods to find that flat ground section that we want to flatten. And the first being, and probably the most important step of the whole process, is to find the point that we want to use. So, the first step is to cycle through all of our vertices, taking into account the radial index, the height offset and width offset, which we will get to later, with explanation for other systems involved in this. And 2, run through and find areas that are either sufficiently flat or the highest point on the base map. You'll get to the base and mirroring system in a moment. That's its own system. By default, however, it will favor the highest point methodology if you set the ground threshold to 0 like I have done, because I found the height methodology to be far more reliable, but the threshold testing system is viable if you can fix the bugs. Assuming that you're doing that, you just simply need to go find the first point in which you can get the within thresholds, and then test the area for the flat ground, extrapolate its center, and then row and center column, respectively, of that area. Assuming that you're using height, however, you just simply get the highest point on the map within a certain row and column. And from there, we simply find out the area of our square based on our radial index and width and height offsets, depending upon what those are. And then from there we estimate a square that we then end up going through, and for that we end up going through a nested for loop over that square surrounding our point. And if it is within a circular radius, one of 2 things happens. If it's within an outer circle, we extrapolate using lerp, the height. Otherwise, we just outright set it if it's more within that circle. And what this ends up resulting in is a nice flat circle of area that's easily distinguishable from the rest of the map. The second system implemented as part of CTF map generation is a mirroring system so that the 2 sides of the map are exactly the same. And to accomplish this, we start with our base and do all of our vertice modifications to the base, and then mirror it onto its opposite side. So when we are creating the mirror, we work backwards through our original base vertice array, creating a unique X point, Y point, and then grabbing an identical copy of the Z point before adding it to our vertices and the UV coordinates for that point, respectively. Making sure also to adjust triangles so that it incorporates our new estimated height, and then informing our map navigation node network forming methodology that we are indeed making a mirror. And the part about grabbing the core vertices is important to creating the encapsulating cliffs, the third system. I will talk more about that when I'm discussing the third system. So when we are making our mirror, we essentially expand the AI Manager's network node generation and to create a second set of navigation nodes, and then to link those that second set of navigation nodes up to our original set if we are indeed mirroring. So the default algorithm mostly untouched except for the corner cases and the top row case. So that way the original network of nodes can connect up to our mirrored network. And if we are still mirroring, we do the same for the new network so that it connects to the old network. Effectively, we've got two networks of navigation nodes that now talk to each other and are thus just one navigation network. For pickups, it's a similar process of finding a node in the base that has at least two connections to it. Selecting a random pickup if one of these nodes are in the middle of our base, or a 5% chance of proccing or generating a pickup at that point. And we can expand this later to incorporate our flag stands. And that's how we get a mirror very simply. The third system implemented as part of creating our capture the flag methodology are encapsulating cliffs for the map so that players and enemies alike do not fall out of it whimsically, or comically depending upon your perspective. To create the cliffs we need a section in which to safely do so. This is where height offset and width offset are incorporated into the map generation as a means by which to narrow down which vertices we want to generate navigation nodes on, and extrapolating those core vertices from the main vertices. However, the cliff generation is all based on the original vertice array, so we don't touch the core vertices until the last step before we implement the navigation nodes. So we start off by figuring out just how much width and height offset we have, and if we have enough, then we can generate our cliffs. And there's actually two options for cliff generations: simple cliffs, which is default, and complex cliffs, like what we see here. And the simple cliffs just target the edge cases, where the row is 0 or the column is either our maximum width or 0, and generates extremely simple cliffs just using the cliff height and modifying the vertices. But if we're doing complex cliffs, we need a bit more calculation, and this is where width offset and height offset come into handy, because we need to cycle through all of the nodes to determine if they are edge cases, bottom corners, or other forms of edge case. So in the bottom left corner we need additional parameters to say if we are closer to our row or closer to our column, to use the width or height offset as the basis for which to lerp our cliffs. That way they are all nice and smooth. And you do need to be careful with some of this, because at one point I did end up creating shall you say, an abyss staring contest. So make sure that that's what happens if these aren't set up correctly. In my case, it took quite a bit of trial and error to get a correct methodology for doing all of this. Essentially, when you're operating in the opposite corner to the base corner, you need to be able to successfully mirror your Z lerping factor, like I have done here. And if we are operating along just the bottom edge, then it's just a simple Z lerping between the row and the height offset. If for columns, it's a similar process but involving the width offset instead. And the core vertices itself is just a really fancy means by which to dictate which vertices have navigation nodes on them, so that way the AI doesn't go trying to scale the cliffs. And that's the cliff system in a nutshell. So to summarize, my project is a capture the flag game mode for multiplayer, and in this video you got to see me undertake a design challenge to generate, or rather create, a map generation method for which to implement capture the flag with. I would go into more detail about how all the individual algorithms work, however, there was a lot of systems implemented, and if you need to, you can pause the video to read through my comments on my code. So, hopefully you can all appreciate just how much of a design challenge this was, because a lot of work went into this.